subgraph of this larger graph. Am I out of time? 5 minutes, perfect. Okay, which I'm not sure it's perfect, but we'll work with it. Okay, so we know these two properties, and so our goal is to show that any graph, which is an induced subgraph of this larger graph, is in graph theory you call this chi-bounded, that there is an upper bound on the number of colors you need as a function of the size of the largest clique. General graphs don't have that upper bound. There's no upper bound on chromatic number or the number of colors as a function of the size of the largest clique. But that it can be true for certain families of graphs, and we hope that it's true for the family of induced subgraphs of this graph that we care about. And why? Let me give you an example of a chi-bounded family, okay, that has this property, all right? So, sorry, this is the last graph theory thing that I'm going to hope to define here. If I have like a path in a graph, like a line of vertices where everyone's connected to the one before it, it's called an induced path if it contains all the edges of the larger graph that have both endpoints in the path. Okay, so like here, this green set of edges and vertices, that's an induced path because every edge in the larger graph that touches one of these vertices is also contained in the path. Okay, so that's called an induced path. Like if there was an edge between this vertex and that vertex, like a blue edge, then this green path would not be an induced path. Okay, that's an induced path. And Giarfas, who's a mathematician, showed that if you have the family of all graphs where the longest induced path has length L, so you don't have induced paths that are too long, then you can always color such a graph with L to the omega minus 1 colors, where omega is the size of the largest clique. So this is an example of a chi-bounded family where you have an upper bound on chromatic number as a function of the clique number. Okay, the family of all graphs with no long induced paths. Longest induced path has size length L. And you might say, okay, that sounds nothing like what you were talking about before. But, oh, and the coloring can also be computed efficiently in this case. But actually, it turns out not to be so irrelevant because now this is not how we get, this is not really how we get our protocols, but you can get a protocol by this argument, and I want to show you how it works because I think it's instructive. Like if we take the graph that contains all the Paulis, okay, so this is a graph with 4 to the n vertices. In fact, that graph does not have long induced paths. That's a graph with 4 to the n vertices, but the longest induced path in that graph is just 2n plus 1. Okay, so that's like logarithmic in the number of vertices. And you can show this kind of algebraically because if you had, basically, if you had a set of vertices that form an induced path of length L, then from them you can construct these products of the neighboring vertices up to 1, 2, 3, 4, etc. So you get L different products, and these are all pairwise anti-commuting. And in a Hilbert space of n qubits, you can't have more than 2n plus 1 pairwise anti-commuting operators. This is a fact from algebra. Okay, so that's kind of the proof of this statement. But the fact that these, so let me show you how you get a protocol from this. Okay, so the longest induced path in these commutation graphs is not too long. It's at most 2n plus 1. So from Giarfas's theorem, which says that that family is chi-bounded, we get that any induced subgraph of this graph that has largest clique of size omega can be colored with at most n to the order omega colors. And that gives a shallow tomography protocol when we apply it to the induced subgraph we care about, where we know that the largest clique has size 1 over epsilon squared. And you know, this protocol has sample complexity n to the 1 over omega 1 over epsilon squared, which is actually not the best we can do for the set of all Paulis. But I wanted to illustrate kind of how these topics of chi-boundedness and tomography connect with one another. And I also wanted to give this example because it has an interesting consequence that we do not get from our other protocol. And so I want to tell you about that consequence very briefly, and then I will wrap up because I think I'm within a minute maybe or 2, 1, 0. Okay. So it has the following interesting consequence, which if you were sleeping, you might still find interesting. Okay. So let's say I want to transmit to you the expected values of all the Pauli observables in a quantum state that you don't know. Okay, how many bits do I need to do that? Okay, how many bits do I have to send you? And I'm gonna allow myself to only transmit them to a constant error epsilon. So epsilon is like a very small constant, like 1/1000th or 1/1,000,000th. So from this shadow tomography protocol, you can infer that there exists a classical compressed representation that is of polynomial size. And I can send that to you. And then given any n-qubit Pauli operator and this polynomial size classical data, you can efficiently extract, meaning polynomial time, the expected value of any Pauli observable up to that epsilon constant error in this case. So that's a funny thing, that you have this compressed representation of polynomial size with efficient retrieval for all Pauli observables. It was not previously known to exist. Okay, and then we do a similar thing. I talked about all Paulis, but we do a similar thing for K-body fermionic observables. This is technically more complicated. It improves exponentially over previous protocols that were based on single copy measurements. And so this is the bottom line of my talk, and I'm ending here. We saw that a fractional coloring is associated with shadow tomography protocols with 1 copy Clifford measurements. But this other notion of chi-boundedness for the family of induced subgraphs of this commutation graph is associated with shadow tomography protocol with 2 copy Clifford measurements. And we use such protocols to get, well, new protocols for K-body fermionic observables and a set of all Pauli observables. Okay, thanks.
Conference proceedings. As introduced, my name is Stepan Fomichev. I'm a member of the algorithms team with Xanadu, and I'm very grateful for the privilege to CQIQC, to the Fields Institute, and to all the organizers to be able to talk to you today about our search for applications of realistic quantum computers. The mission of Xanadu is very helpfully printed on the wall in case that we ever forget. And it is that we are to build quantum computers that are useful and available to people everywhere. And for the purposes of today's talk, I really want to focus on this useful part of quantum computing. And let me just start by saying that we already have in the field, in a number of different organizations, a lot of different quantum computers out there. And they are already serving a very useful purpose of advancing fundamental science, of helping us understand better the principles of quantum mechanics, of educating the new cohorts of students about those principles, and also just serving to inspire many people around the world about quantum science. But for the purposes of today's talk, what I would like to focus on is how different researchers and engineers across the various industries could use these quantum computers to attack the challenges that they're facing in their research or engineering of various products. So really on the commercial utility and value of quantum computers. So that begs the question, what are quantum computers for from that perspective? A number of researchers have already thought about these questions over the years and have given a number of different answers, some of which I have included here on the slide. But I think we would all agree that there is still an appreciable gap between the demands of the algorithms that fall into these various domains and a lot of the others that I haven't listed here, and the available quantum hardware that we have access to today, and even the hardware coming in the next generation that we would be able to have access to soon. Just to make this a little bit more concrete, let me give you a couple of examples of the current costs of algorithms in a couple of different domains, and I will talk about their costs in the following way. So we'll look at the number of non-Clifford gates that a given application requires, and we've already heard a little bit about Clifford gates earlier today. The non-Clifford gates are these operations that are not efficiently simulable with classical methods. And so they really characterize the quantumness of the kind of calculation we'd like to carry out with the quantum algorithm, and they should be ultimately responsible for giving us some kind of advantage. Let's also take a look at the number of logical qubits that our application requires, where by logical qubit we mean some kind of collection of physical qubits tied together through an error-correcting code, such that it is able to maintain coherence long enough for us to carry out the algorithm calculation that we're interested in. And finally, let me add the column for runtime, which I will approximate very, very heuristically by just saying that the runtime is the number of non-Clifford gates divided by some kind of clock rate that we assume for our quantum processor, and let's just take that for the sake of argument to be 1 megahertz. There was a very nice paper, a corpus of 300 plus pages that recently came out that has very helpfully done a lot of the work of compiling all of the efforts that have gone into applications and quantum algorithms over the years. And I show them, some of them to you in this table. Just like this. Great. So what you can see from a lot of the numbers that I've highlighted in red here is that a lot of them are quite large. The number of logical qubits that seem to be required for fields such as material simulation, catalyst, drugs, cryptography, and even finance seem to be way outside of the reach of the present devices, but also of the devices that we expect to come in the next generation, the early fault tolerant regime. And the same goes for runtime. You can feel free to disagree with these numbers. I personally disagree with a lot of these numbers on any given day, but I think we can all agree that there is still a significant gap between the demands of the algorithms and the applications that we're looking at and the kind of hardware that is available and even is coming to us in the next generation. For reference, the kind of hardware that many companies seem to be aiming towards in the coming few years is something on the order of tens to hundreds of logical qubits and significantly deeper circuits than we can perform at present, but still fairly limited, maybe something like 10 to the 6 or so non-Clifford gates. And so what we can conclude from these two sets of numbers is that the algorithms and applications are really not ready for the coming generation of early fault tolerant hardware. We haven't really been able to figure out what will we do with those devices once they're available to us. And this is really an important challenge for our field of quantum computing because ultimately the commercial success of these devices is going to be very important for the continued operations of all of the different members of this industry. So one way that we at Xanadu like to think about how we could make progress given these stark restrictions is by giving ourselves a quantum budget within which we'll construct algorithms and applications. So let's first start by saying that we will make sure that our algorithms and applications require no more than 500 logical qubits. This number comes from essentially thinking about how many different organizations are now talking about aiming for something like 1 million physical qubits in the coming few years. And with a typical surface error correcting code, that can translate into something like 1,000 logical qubits. So if we want to be a little bit more conservative, let's just divide that by 2 and say 500. We will also limit ourselves to no more than 10 to the 8 non-Clifford gates per circuit. So the non-Clifford gate depth shouldn't be more than 10 to the 8. This is also tied to the kind of expected performance of the new generations of devices. Typically, if you have something like 1,000 logical qubits, you might be thinking about an error correcting capability of 1,000 squared, so 10 to the 6 or so gates that you can execute coherently. However, we didn't put 10 to the 6 here because, of course, there's sort of a lower bound on how many non-Clifford gates you should be using in order to actually extract some kind of value from your quantum algorithm, right? And certainly, there's no way we can get enough value with just a single non-Clifford gate, right? And similarly with 10 or 100, it's very difficult to see how we could outperform classical simulation methods. So from combining that with the kind of capabilities we expect, we put that number at 10 to the 8. And then finally, let's say that the total number of non-Clifford gate operations, we'll set that to 10 to the 11. And we can think of that as translating it into runtime. Again, using that 1 megahertz clock rate, that amounts to about 1 day of runtime. So let's just go with that as the number. And let me just quickly note that we're far from the only ones who are thinking about translating quantum algorithms into real-world applications so that they're ready for the next generation of quantum hardware heading our way. In fact, Google Quantum AI just earlier this year announced a new X Prize that is offering money to different research teams and organizations specifically to target that regime. And we think this is a very exciting research opportunity to be focused on devising new algorithms and applications specifically for that kind of early fault tolerant regime. So what can we learn from having set this quantum budget? Well, for one thing, we at Xanadu think that these sort of restrictions really mean that we should focus on something like quantum chemistry as the domain of application. For one, this is because we think of quantum chemistry as a set of applications that has a possibility for quite broad impact across a number of different industries. And at the same time, we have somewhat more control than, say, in a field like cryptography over the sizes of the system. So it's going to be a little bit easier for us to fit within the budget that we've set for ourselves. At the same time, we can also recognize that we need that innovation in the regime of what we like to call ISK, what is also called early fault tolerant quantum computing regime, where we need to start designing quantum algorithms and applications specifically for that few logical qubit, slightly different circuits kind of regime. And this is work that is already happening, and it's very exciting to see all of that progress. And we just want to pile on more in that direction. Another thing the budget does for us is that it kind of allows us to shift our mindset from, okay, this is the problem we want to solve, how much do we need for a solution, to, well, no, this is the device, this is its characteristics, what can we do with the given budget that we have? So in the words of famous physicist Angus MacGyver, if what we need to do is to have a plane take off and all we have is a paperclip, let's not give up and let's see how high we can get that plane to go up with just what we have available. Finally, because of the limits on the number of qubits, we need to be able to focus on problems that are small. We're probably not going to be able to find advantage just by outcompeting the classical methods on size, but where we should look for advantage is for small and hard problems. And in quantum chemistry, that would translate to something like correlated or very entangled problems, where we can really make use of all of the things that quantum algorithms have to offer us. And finally, because of these restrictions and budgets, really the quantum algorithm will be kind of a little piece in a bigger puzzle comprising classical simulations, experimental work, that all works together to give us some kind of an advantage, at least in the early stages. So now that I've told you about this idea of setting a budget and kind of working backwards from that, let me give you an example of a research project that we were undertaken in this vein and how that has inspired us to make kind of different choices about the application we pursue and the design of the algorithm that goes with it. And the example I want to give you is X-ray absorption spectroscopy for batteries. This is a very high-level schematic of a battery, and the main thing to take away from this is that it has two key components, a cathode and an anode, and there's a separator in between. And what the separator is responsible for is that it allows the flow of ions, let's say lithium ions, through it, but it doesn't allow electrons to flow through it. And so electrons are forced to take the long way around, passing through whatever load we want to put on our battery. So, of course, we always want our batteries to be better. One of the things that we want them to be better at is having more capacity, higher energy density. And there's a lot of work in that direction. That one particular family of materials that is being considered for this are the so-called lithium excess materials. And as you can see, they have fairly nice characteristics across a large number of parameters. However, it turns out that they have quite poor cycle life. So what ends up happening when researchers build these devices is that over time, as you charge and discharge your lithium excess-based battery, its performance is slowly degrading on the scale of a few days or a few dozen charge-discharge cycles. And it's not entirely clear at this point what is behind this degradation. One hypothesis is that as we charge the battery and as we remove the lithium ions, which are here in green, from the lattice, we have these cavities that appear in the cathode. And what our oxygens might be inclined to do in the presence of these cavities is they might want to, missing their old bonding partners, they'll try to bond with each other, leading to something called oxygen dimerization, which is concomitant with a change in the oxidation state of the oxygen atoms in the lattice. So that's one explanation. Another explanation is that perhaps it's nothing to do with the oxygens, it's the transition metals that change their oxidation state. And the details here are not so important, but a very similar thing happens. So the structure of the material changes, and once we've removed the lithiums, we can no longer put them back in, which leads to the degradation of the battery performance. It's very tricky to characterize what is happening in the bulk of this material with the experimental methods that are available, but we noticed that in both cases, there should be a change to the oxidation state of one or the other species comprising the cathode. And so if we had an experimental technique that was able to probe these things, then we might be able to deduce whether these changes are occurring and thus what kind of structural changes happen in the crystal lattice. As it turns out, X-ray absorption spectroscopy is exactly the technique that gives us access to this information. X-ray absorption spectroscopy is similar to other kinds of spectroscopies. You have a sample and you bring it to a synchrotron that is able to generate a source of X-rays for you, and you shine your X-rays through the sample and you look at the absorption spectrum that results from this. The interesting thing about X-rays is that they're very high energy beams of light. So when they come in, they don't actually excite the kind of electrons that are close to the Fermi energy. They go ahead and knock out the very deep core electrons and bring them all the way up to the valence band. And why is this interesting? Well, because core states are actually quite tightly bound to the atom around which they're centered, that means that the kind of excitations that appear in this situation are similarly going to be local. And that means that X-ray absorption spectroscopy is then a local probe of electronic structure surrounding a particular atom. And oxidation states are precisely one of those local electronic properties that we might be able to probe with this technique. One way in which this is done is using a technique called fingerprinting. So you have a number of reference spectra that you've collected for materials where you know what the oxidation state is, and then you use them to fit the overall spectrum. So on the example of magnetite, let's say we want to figure out if we have iron 2+ or 3+ in the structure, we go ahead and collect some X-ray absorption spectra for configurations where we know what the iron oxidation state is, let's say 2 or 3, and then we put them together as a linear combination to fit the spectrum for the actual material of interest. And then from the percentages of the linear combination fit, we read out how many of the different kinds of oxidation states we have in the material. So that seems pretty straightforward. Why can't we just do that with lithium XS? Well, the problem is that the spectrum itself is very complicated. And in particular, the reference spectra that you might use to do the fingerprinting might have effects that change the spectra beyond the oxidation state. Details of the geometry, the fact that you might be using different elements to obtain that reference spectrum in the first place. And sometimes you simply have no reference spectra at all. So that is what is leading to the need for ab initio modeling for these spectra. How do we do this? Well, we take these local clusters, and they're local because the X-ray absorption physics are quite local in space because we're exciting core states. We construct an active space by selecting some of the electronic states to excite, and then we evaluate this absorption cross-section, which ultimately depends on dipole matrix elements and excited state energies. And this is the point where we start to get excited because we're looking at a relatively small system where I need to attack a whole supercell here. And it's still looking quite hard and correlated because we're after excited states and not something like the ground state. And it turns out that classical methods to study this problem are actually facing some challenges. So on the kind of density functional theory side, you might be missing some multi-electron excitations. Whereas if you're looking at something like post-Hartree-Fock, then these methods just fail very prohibitively with system size, so that you're not able to add enough orbitals into your active space to get a nice agreement. And this is the place where we expect quantum computing to come in. So the proposal that we have to target this problem is we take our samples, we characterize them with X-rays to get some kind of sample, and then we guess a number of different structures with different oxidation states whose spectra we then obtain by simulating them on the quantum computer in the way that I was just describing. And then once we have these spectra, we can do the kind of fingerprinting procedure and then determine the oxidation state of oxygen or manganese or other constituents. And then once we know that, that can help us engineer around the structural challenges that occur. And if you'd like to see more details, please check out our recent manuscript about this. So the quantum algorithm that we use to obtain this, they all start with the preparation of the ground state. And because the clusters that we're looking at are fairly simple, they're not too challenging to prepare. We know from the literature that these ground states can be prepared fairly accurately. And then we have a choice. So we could rephrase the absorption spectrum as a Green's function in frequency space, and then we can use a Hadamard test circuit to obtain the values of it. The challenge here is that we have to implement this resolvent, and that leads to something like an HCL algorithm or a different approach to doing this, but it requires a lot of ancillars, and it generally is kind of expensive to do. We might also think about just using directly quantum phase estimation. That's also something that we can definitely do. But ultimately, we're deciding to go with the Green's function in the time domain, which in some sense has the smallest number of ancillars that we need to use, and also is doing kind of one of the most natural things you might want to do on a quantum computer, which is just preparing some state and then evolving it with respect to the Hamiltonian. And then we can do all the kind of classical post-processing afterwards, taking the Fourier transform and all that. So the final punchline here is that we can do a resource estimation for this approach, and it seems that for a single run of the algorithm, all we need are about 10 to the 8 non-Clifford gates per circuit. Unfortunately, we do need quite a large number of qubits coming from the overhead of qubitization. And what we're currently doing now is we're pursuing simulations and optimizations of the algorithm. So we're on the right here, you're seeing a full end-to-end simulation of an absorption spectrum of this particular small molecule with 4 hydrogen atoms. The nice agreement between the classical and the quantum results is telling us that the algorithm is benchmarked and it makes sense. And the simulation is being done using Trotter-based methods, not qubitization. And the advantages of this is that there's no qubit overhead. So if you need 30 qubits to describe the system, that's all you need. We know that Trotter-based methods often have a reputation for being quite expensive, but this is typically based on analyzing them with asymptotic bounds. So when you actually go ahead and do empirical simulations of the algorithm, you figure out that you actually need quite a bit fewer gates than you were expecting you would need. So just to summarize with a couple of key insights from this example, first of all, we are really advocating the search of application as a way to reduce the costs of the algorithm. Finding a kind of niche application goes to a long way to reducing the number of qubits and gates that you need while still maintaining competitiveness with classical methods. At the same time, because we're after spectra, something like dynamics, time evolution of the initial state, as opposed to something like the ground state, that also makes quantum algorithms more attractive in practice. As I was saying earlier, and these are results from a different research group, but we see something very similar, is that in practice, the empirical costs of pursuing a Trotter-based time evolution approach is significantly smaller than the various analytic and even commutator bounds that you might expect for it. So we always really advocate for using large-scale simulations as a way to assess the cost of the algorithms and to try Trotter when in doubt. And then finally, in this particular case of X-ray absorption spectroscopy, it was really the locality of the XAS physics that reduced the problem size for us. But even if that's not the case, you can use techniques like embedding to really kind of zero in on a few of the most strongly correlated states in your material and use the quantum algorithm to really attack that problem, and then integrate it with pre or post-processing with classical methods. And with that, I thank you very much for your attention and just want to advertise that we are hiring. So if you have any questions, please let me know. I'm happy to talk about any of this. Thank you.
Thanks for a fascinating talk. We have time for